Continuing on our theme of mass destruction of the Earth's surface, we're going to focus on climate change for a bit. And in particular, we're going to talk about catastrophic changes. Now, the first thing we're going to discuss is the acceleration of climate change by albedo feedback. This is a positive feedback that you can see depicted here in this GIF. As the sea ice melts at the high latitudes, the Earth's surface becomes less reflective. As that surface becomes less reflective, it becomes more absorbent. In this case, it's absorbing incoming radiation, insolation from the sun. As that ice goes away, the Earth's surface becomes darker, and as the Earth's surface becomes darker, it acts more and more like a black body. So literally, we're going from a white body to a black body. Now, this is going to include destabilization of continental glaciers. So we saw in the last lecture an alpine glacier in Norway that's retreating, alpine glaciers in Montana that are retreating. We also see significant drawback or pullback of ice sheets that are at the high latitudes, such as Greenland, the ice caps in Iceland, the ice sheet in Antarctica. As those become destabilized and break up, they further change the albedo of the Earth, making the Earth even darker. One of the outcomes of warming is the carbon release from permafrost. Again, in the last lecture, we saw an example of permafrost destroying a village in the Arctic. In addition to the melting of this permafrost and the destruction of infrastructure, we have the release of carbon that's been stored in that permafrost for a very long time, since the Pleistocene, maybe earlier than the Pleistocene. Once that organic carbon in the permafrost warms up, methanogenic bacteria principally consume that organic matter, producing enormous amounts of methane. So we're releasing this carbon from the permafrost into the atmosphere in the form of methane, the worst greenhouse gas, the worst common greenhouse gas. Now, another alternative scenario is release of carbon from seafloor sediments. These are known as clathrates or gas hydrates. We won't go into exactly what they are in this course, but they're a kind of weird methane ice that forms under specific temperature and pressure conditions. If those temperature conditions were to change, rising sediment temperature associated with rising seawater temperatures is going to cause this clathrate to change phases and go directly from a solid phase clathrate to a gaseous methane. This is an idea that a friend of mine came up with in graduate school that probably describes the warming event that took place 55 million years ago. There was another incident more recently, around 7,000 years ago in the North Atlantic, the Storegga Slide, an area underlain by gas clathrates of about the size of Iceland, suddenly destabilized and bubbled up to the surface, and the whole shelf, a shelfal area off the coast of Norway the size of Iceland, just collapsed into the North Atlantic. So that would be a big blast of methane into the atmosphere. That's probably not going to be as significant as the permafrost melting, but it will likely be significant. And we may see a reduction of the thermohaline circulation as ocean waters change in salinity, chemistry, and temperature. That's going to result in a change in the physical state of that water. Therefore, the way it circulates, the way it may replace water at the bottom of the ocean and where it may upwell. So there are going to be changes in thermohaline circulation, perhaps a reduction in thermohaline circulation, which is going to lead to a destabilization of the atmosphere because the atmosphere is going to have to make up for that heat transport that the ocean is no longer responsible for. In terms of ocean acidification, again, we touched on this in the last lecture, approximately 30% of CO2 emitted by humans is absorbed by the oceans. Numbers such as 40% and 50% are thrown around. This is something that I worked on as a graduate student back when I first started graduate school in this part of the world, the Bahamas and Florida Bay and the Florida Keys. And what we were working on was the reaction of seawater and carbon. In this case, carbon dioxide reacts with seawater, forming carbonic acid, as we've seen a number of times in this course. What we haven't seen is that chemical reactions can leach carbonate ions from seawater, and these chemical reactions can also inhibit the ability of organisms to pick up important nutrients like iron and phosphorus potentially. Increased acidity inhibits calcification processes for sea creatures. Again, we saw that in the last lecture. Makes it more difficult to make calcium carbonate as the pH goes down. Now, when we talk about pH going up or down, again, one thing to consider is the pH scale is the anti-log of the hydronium ion concentration. So it's a logarithmic scale. Any small change in pH is a very large change in acidity and a very large change in the amount of CO2 that's absorbed. So here we see this in action, the Keeling curve that we're all familiar with. And seawater PCO2, this is going to be at the surface. So we're measuring the amount of CO2 that's dissolved in the seawater at this station, located not too far from Mauna Loa, the site of the Keeling curve. Associated with this change in seawater PCO2, partial pressure of carbon dioxide, is a change in the pH. So as the amount of CO2 that's absorbed, it goes up, the pH goes down. And again, it only takes a tiny change in pH to significantly alter the chemistry of the ocean and significantly alter the ability of organisms to live in that ocean. If you've ever had an aquarium, either as a kid or now that you're grown up, you'll know that a freshwater aquarium is much easier to take care of than a saltwater aquarium. And part of it is this whole business, maintaining the proper pH in your aquarium. Whether it's fresh or saltwater is important. Saltwater is even more important, usually. There's a predicted change in sea surface pH that we go back to scenario A to see the grimmest of scenarios, a very large increase in acidity here at the high latitudes. And that's in part because the buffering capacity at the high latitudes is less than the buffering capacity, the ability to absorb acid without changing pH. That's buffering, roughly. That's going to be more difficult to maintain a stable pH at these high latitudes than at the lower latitudes. But we're active in biodiversity ways as well. Humans have altered the Earth's biosphere since we appeared on the Earth's surface, initially just by bothering a few plants and animals in our region, and subsequently in the 1700s, we got much better at it. We were starting to mechanize farming. We were starting to establish larger farms run by a smaller number of people, such that by 1750, we still occupied less than 10% of global land. In 2000, 250 years later, we went from less than 10% of global land occupation to 60% global land occupation. This is 21 years ago, so I suspect it's much worse than this now. Cropland use over the long term, in this case from 1600 to 2016, again, we don't see much of a change until an inflection point right here at about 1700. And then we see an increasingly rapid rise in land use until the 1950s, and it's starting to level off now. But it's still rising. So leveling off is relative. We're still going up. In fact, now, more recently, we're on an uptick. And again, this is because population is rising at a tremendous rate. Land used by rangelands and croplands have increased over this 250-year period, as has the area occupied by cities. And the result is semi-natural and wildlands have decreased accordingly. So those are now below 50%. Again, we've taken over 60% of the land for our purposes, and we've left the steeply sloped mountainous areas alone for the most part, except for deforestation and mining. Okay, so now we're moving into the Anthropocene, or the age of man. This is variably described. Here it's 1780 to present. It has been described as starting 12,000 years ago. So for our purposes, to keep it simple, we'll just go with what the book says and say 1780. In this time, we've deforested large areas. We have caused the mass extinction of many, many species. And our activities have affected the biosphere almost in its entirety. Here we see an image of the border of Haiti here and the Dominican Republic here. You can easily spot the border by the presence or absence of trees. The trees on this side of the border have been harvested for initially hardwood, but then ultimately for charcoal for cooking. Dominican Republic is a bit more developed, hasn't been destroyed by colonialism to the degree that Haiti has, so it's faring a little bit better. It's still not a natural environment by any means, but it hasn't been totally devastated like the Haitian side of the border. Why do we need to call this new period of geologic time the Anthropocene? Why do we need a new period of geologic time? Well, because like all other periods of geologic time, they're marked by extinction and evolution events. Right now, we're in a downturn in terms of biodiversity, a major downturn. Thus, we are ourselves responsible for the current mass extinction. What we've done has changed the Earth's surface. We've begun the mass extinction, the sixth mass extinction. The problem really is, an esoteric one between scientists. Where do we mark the beginning of this age? I mentioned 12,000 years ago is one idea. 10,000 years ago is another idea. 1750, 1780, take your pick. Just pick a point where you've decided that people have done enough damage that they represent or they deserve their own geologic period. When we look back in time, we again start with the oldest rocks on Earth, about 4 billion years old. The oldest minerals around 4.4 billion. And we get to the oldest fossil cells between 3 and 2 million years ago. Evolution of eukaryotes before 1 billion years ago. We have the first mass extinction caused by glaciation at the end of the Ordovician period here, the Hernanchian event. And then a series of other mass extinctions. The end of the Devonian, the end of the Permian, end of the Triassic, and the end of the Cretaceous. Things have been proceeding naturally up until the Anthropocene. And here it's described as the sixth mass extinction. So what's the problem? Is it a big deal or is it not a big deal? It's a very big deal. We face daunting problems. The continued use of fossil fuels means we're going to double CO2 in the atmosphere in the next 50 years. An extraordinary collaboration of scientists, leaders, and the public is needed. You can imagine how well that's going to go. Politicians, people, and scientists. We all get along great. Everyone can easily come to an agreement. Good luck. So what do we need to do? We need an energy policy. We need a goal. We need something to focus on, something that we can achieve. So an energy policy that is protective of the environment, protective of our interests, our needs as a modern technical society. And that's going to require the use of alternative fuels. We can't keep burning oil and coal and anything else we find in the ground that's flammable. That's unsustainable in the world that we like to live in, at least the world I like to live in. So this is going to require re-engineering of the carbon cycle. Maybe get rid of most of the carbon cycle. And we're going to need to stabilize carbon emissions. We have to stop pumping CO2 and methane and nitrogen compounds and CFCs. We've cut most of those back, but not all of them. We need to cut these all back. We need to control them. We need to calm down. This calming down is going to include improve energy efficiency and reduce waste. The many first world countries are approaching this in a pretty significant way. Proper pricing of fossil fuels will lead to a change in energy efficiency and waste, because if we increase fossil fuel costs, this will allow people to transition more readily to new technologies. Part of the cost of fossil fuels is their support. They receive tax incentives to do their thing, to be oil companies, to be coal companies. Tax benefits allow these companies to be profitable. If we take away those, then it's more of an even footing between new technology and old technology. And this is going to require international agreements that help developing nations. They don't have the money and the technology that developed nations have. So they need help in other ways. We can provide them with new technology, and we can provide them with some support while they adopt this new technology. Now, it's important to know that no single fuel is going to replace fossil fuels. There's no unobtainium that's going to power our future. We have to look into lots of different things. These different things include solar. There are a number of different ways that we can use solar power. Talk about that a little bit in a coming lecture. Wind power is pretty obvious, and biofuels. The biofuels that we're playing around with now are kind of bad examples, but that's what's making the grade at this point. So ethanol from corn would be an example of something that's bad in that it uses about the same amount of fuel as it generates, but the fuel it generates has a lower energy content, so ultimately it costs more to make biofuels than it's worth. Biofuels cost more than regular fossil fuels, and they use fossil fuels to create themselves, to create biofuels. fossil fuels are used to create biofuels, defeating the purpose. There's potential for an increased use of nuclear power. Modular nuclear reactors, they're small, they're not as dangerous as larger nuclear reactors. They can be set up to power thousands of homes, not necessarily millions of homes. In some communities, that's going to be the way to go. And we're going to need to change our land use policies. If we can encourage reforestation, for instance, we bring the albedo back to where it was, at least closer to where it was before we messed it all up. And there's a possibility that we can use fertilization of the marine biosphere to grow carbon-consuming organisms. So throw a bunch of plant food into the ocean, essentially, and the plants go wild. When these plants go wild in the surface waters, they pull CO2 out of the surface waters, pulling more CO2 out of the atmosphere, pulling CO2 out of the deeper water. And if we sink that organic matter and bury it in the sediment pile, then it's out of the picture, for the time being at least. So we're managing the carbon crisis by taking carbon and putting it back in the ground where we found it in the first place. Another example is carbon sequestration, where we're capturing CO2 at the source. So in this case, a coal power plant. We take that CO2 that's generated from the power plant and we pump it back into the ground. In this case, we're pumping it in the ground to push more oil up, which we're going to burn, creating more CO2. Eventually, we're going to run out of profitable stuff that can be pushed out of the ground by CO2. Other CO2 can be injected into deep saline formations. Again, this is kind of like throwing all of your garbage in your backyard and covering it with leaves and some dirt and saying, there, problem solved. It can make its way back out from many of these temporary traps that we place it in. I don't know that that is ever going to become significant. We have CO2 uptake by forests, biomass plantations, and restored lands. Now for forests and restored lands and biomass plantations, it's a bit of a smoke and mirrors, three-card Monte kind of situation here, in that CO2 will be taken up by these forests, biomass plantations, and restored lands. But when this vegetation dies, most of this CO2 goes back into the atmosphere again. So it's a repository. It's certainly nice to return land back to its natural state. So no problem with that. The problem, the bait and switch of saying it's going to absorb the CO2 and the problem solved, that's just not realistic. It's not math. Well, it's math, but it's bad math. This is something I hadn't seen until I received this book a couple weeks ago. Stabilization wedges to offset the growth of carbon emissions. Each slice of the wedge must be reduced to meet emission goals. Stabilization at current rates would reduce but not eliminate climate change. What are these wedges? Hey, there they are. This brings us to the wedge diagram at the end of the chapter. I've looked it over. It's the first time I've seen it. It is a confusing, kind of messy bunch of data. I did a walkthrough with it. It takes about a half hour to explain what's right and what's wrong about it. And given that many of the things are unlikely to ever come to pass, I think it's better we just let it pass by the wayside. So we're going to skip that whole thing as far as the exam's concerned. You might want to take a look at it just to see what they're suggesting. That's okay. But the numbers are kind of wonky. And again, it's a rough one. We'll just end the lecture with that.